So today we discuss motional electromotive force. Motional EMF. Motional means the coil are in motion. If the coil are in motion, what will happen? So suppose there is an external magnetic field B. There's a cross. Cross represent towards the board. Okay, there's a cross. That the external magnetic field. Now a coil. Suppose a coil. Okay, coil. These the coil. These are the coil, and the B, suppose the cross. Okay, and there's a magnetic field region. Okay, there's a magnetic field region, there's a coil, and then you see that very carefully. This coil, someone hold that coil. Okay, hold the coil, and moving towards the left side or right side. So obviously there is a velocity, the motion. Obviously this is a motional EMF. So that is a to and fro motion, front or back motion. Okay, these are the motion. Okay, now if there is a motion, so obviously there is a force associated, that's called F1, that's called F2, and that force is called F3. So there is a force, and suppose this length be L, and this length be X. Okay, and suppose this magnetic field region, that is a B, and these are the motion. Okay, horizontal motion. So a horizontal motion, so field will change because X is variable. Here X is variable. Okay. So you see that X is changed. Okay, now if there is a motion, so there is obviously current, so that is a I current. Okay, so we know that the actually change, so area. Okay, these are the area with a change randomly, and if the area is changed, so flux also change. So phi B is flux also change, that is BA cos, and the angle be that 0 degree, cos 0 be the 1, so that is BA. So that is a B, there's a B, and area means these are the length, L, this length also be the X. Okay, that is LX, that is phi B. Now we differentiate both sides with respect to time t. So d phi b dt, that is equal to bl dx dt. You see that x is variable, so L and B are the constant. You see that this coil is moved, so obviously there is a x be change like that. So this coil move here, and now x, this length x, but L be the same. These are the L be the same, but x be the change. Now put minus side in both, and these minus, and you choose the n number of turns, so the n be the 1. So d phi b dt we get EMF, that's the EMF with minus sign, that is equal to minus, and these minus after derivation, derivative after, so to and fro motion, so the minus with the cancel, that is BL B. V is the velocity, so dx dt. So in that direction, suppose is the origin, so origin to right side be that is suppose call a plus x, and left side is a minus x. That's the differentiation. I get a remove here minus sign. So EMF equal to finally get BLB. Okay, and that EMF is called induced EMF. This EMF is induced EMF. Okay, and there is obviously induced current. These are the induced current, and this induced current, and that induced current the I, that is equal to from Ohm's law, that is EMF by R. okay, and that is BLV by R ampere. That is the induced current. And now is the work done. What is the work done? And suppose there is a work done means a charge, a test charge. So consider a test charge, okay, moving from this point to that point, this point, okay. These are the here to there, that point. A moving a test charge, moving a test charge from, suppose these are the called A, B, C, D, B to C. Probably there is a work done, and that work done, that is equal to a test charge times EMF, a potential. Now that is a test charge, and we know the EMF equal to BLV joules, get work done. Okay, so now we consider there is a force, electrostatic force and magnetic force. We get a Lorentz force, that is a QE, that's the electrostatic force, plus Q V cross B, the magnetic force. If I combine these two and common the Q, that is equal to E plus V cross B. Now, if there is a no motion, suppose this motional electromotive force has no motion. So, if suppose there is a no motion, so V be the 0. If velocity be the 0, that is equal to Q E plus 0 cross B, and 0 into something will get 0, that is this force is now electrostatic force. So there is a no magnetic force. So if there is a no motion, we conclude, okay, so there is a no magnetic force, only electrostatic force are present. Okay, force present. So obviously there is a motion is very important for magnetic force. Motion, so motion is important for FB. Okay, very important. For magnetic force, motion is very important. Clear? That's the motional electromotive force. Now we recall some previous chapter concept here. So that is previous class concept, that is self-inductance and mutual inductance. So what is, just recall previous class, self-inductance and mutual inductance, and what is inductance? Inductance. So concept is, what is inductance? So question is, what is inductance? And discuss the concept here. Suppose there is a coil. Suppose there is a coil. Suppose there is a coil and current passing through that coil I, and there is produced a magnetic field. Okay, magnetic field inside the coil. Okay, these are the magnetic field inside the coil B, and you see that the field obviously inside the coil, okay, not outside. These are the inside the coil, okay, and each winding produces a magnetic flux, and each winding, current passing through the each winding, okay, and each winding, okay, each winding produces a magnetic flux. So this magnetic field crossing the central region of the coil. Okay, and now there is another term, it's called flux linkage, because the number of windings is very important for holding a maximum number of flux. So N very important, that is N phi B. This is called flux linkage, that is directly proportional to I, this current I. Now if I remove that proportionality sign, we get some constant Li, and L is called inductance. So inductance equal to N phi B by I. So SI unit of inductance is, okay, and also called self inductance. This is also called self inductance. That is equal to the phi B. The phi B is the B dot A, means Tesla per area means meter square, I means ampere, and number of turns, so there is no unit here. So Tesla meter square per ampere, that is the unit of self inductance or called inductance here, and this called another name is called Henry. So 1 Henry, that is equal to 1 Tesla 1 meter square by 1 ampere. That's a 1 Henry. Okay, so there is a two types of inductance discussed mainly, the self inductance and mutual inductance. Okay, we discuss the two types of inductance, self and mutual. So here the self inductance this diagram is, see the very carefully. These are produced as self inductance. These are L, also called inductance or self inductance. Now in this equation, N phi B equal to Li. Now we differentiate both sides with respect to time t. So we get N d phi B by dt, that is equal to L di dt. Now the minus in both sides, put minus. So N d phi B dt from Faraday's law, that is equal to EMF, and that is minus L di dt. That's the EMF. Okay, this is called self-induced EMF. This EMF is called self-induced EMF. Okay, and so what is the mutual inductance? Now the question is arise, if there is a self-inductance, so what is the mutual? So self means own, and this current passing through the own coil, a coil also produce a magnetic field, and this current produce when another coil, okay, when another coil produce a magnetic field, some part of that coil magnetic field crossing this magnetic field, this B, and produce a own produce the induced current, and that induced can also produce a magnetic field that actually opposes the source of that magnetic field, of that coil of that magnetic field. Okay, now here we see that the mutual inductance. So clear the concept when I discuss the mutual inductance. The concept is very clear. What is self inductance? Self means own here. So mutual means there is a two coil. There is a two coil. There is a two coil. This is called coil number 1, and I choose another coil. There is a galvanometer, and these are the coil number 2, and you see that the current passing through the coil 1, I1, and the number of turn in coil 1 with the N1 and produce a magnetic field. Okay. This coil produce a magnetic field. Okay, so now the sum part of this magnetic field crossing the coil 2, inside the coil 2 obviously. Okay, there's inside the coil. Okay, some other inside the coil 2, and now the number of turn here coil 2 be suppose the N2, and the flux coil 2 due to coil 1, the coil 2 due to coil 1, and these are the B1. Okay, coil 2 due to coil 1, the flux linkage of coil 2, that is N2 phi 2 1, the flux linkage of coil 2 respect to coil 1, that is equal to some constant mutual inductance same as a self inductance, both concept be the same. Okay, suppose mutual means that current produced with the help of or produce a magnetic field also produced with the help of other coils, so that's why these are called mutual inductance. So they are mutually dependent to each other. Okay, self means there is a independent. Okay, 2 1 mutual inductance of coil 2 with respect to coil 1, because the current passing through the coil 1. Obviously, after that some magnetic field passing here. Now, if any one of their relative motion, so obviously there is a current. Any one of the coil are in relative motion. Okay, if there is any one of these two coils are in relative motion, so obviously there is a current here. So now the current is I1, and now if I differentiate both sides. Okay, suppose N2 with respect to time, phi 21 dt M21 di1 dt, and put minus sign, and this minus N2 d phi 21, the flux crossing to coil 2, and these magnetic field produced by coil 1 and dt, that is EMF 2, that is equal to minus M21 di1 dt. Okay, so here is a reverse case. So reverse case means, so reverse case, so that's a reverse case, so that the reverse case is, so current produced in coil 2, okay, current produces coil 2, and C1 own mutual inductance. Okay, C1 here produce a mutual inductance. So now the mutual inductance of coil 1, that is a coil 1, obviously there is a phi coil 1 due to coil 2. So the flux linkage of coil 1, that is equal to here N1 phi 1 2, and the mutual inductance of coil 1 with respect to coil 2, the current passing through coil 2 I2. Now we differentiate both sides with respect to time. N1 d phi 1 2 dt M12 di2 dt. Now minus both sides, that is EMF of coil 1 minus M12 di2 dt. Clear? Now, if I let us assume that if both mutual inductance are same, so let us assume, let us that M12, that is M21, that is equal to M. Say, okay, so the EMF 2, that is minus M due to di1 dt, and EMF 1 minus M di2 dt. That's the mutual inductance, mutually dependent to each other. Okay, that's the mutually dependent to others coil. That's why these are called mutual inductance. Okay, now we discuss the most important concept, that's the AC generator. Okay, what is AC generator? So the AC generator is an important application of induction. Is a important application of induction. Is actually a machine. Okay, and there's a AC is alternating current. So Nikola Tesla, okay, the famous scientist Nikola Tesla described the basic principle of that machine. Oh, Nikola Tesla described the basic principle. So what is the basic principle? Before that, we draw a AC generator. Okay, so these are the magnet, north pole, that is south pole. Okay, and there is a coil or called armature. The another name is coil or armature, both same. Now there is slip ring. There is a two slip ring here. This length is connected this ring and this small connected in that. These two slip ring, and now these are the carbon brass and measure output or EMF here. Output at these two terminals. Okay, and these are armature coil, these are magnet, and these axis. Okay, and this is also called axle. Okay, and there's green color line is called slip ring. Okay, and these are the carbon brush. Okay, so here and the very important, that's the effective area. These are effective area of coil or armature. Very important. These are the effective area of coil or armature. Okay. So the Nikola Tesla actually described that the induced EMF, these are the induced EMF or current in a loop, or there is a current in a loop. Okay, these are the loop or armature here. Okay, current in loop or armature. Okay, and through a change its effective area. So if the coil is rotated, so effective area will be changed. So the effective area mainly change. Okay, so the induced EMF mainly depending on the effective area. So the Nikola Tesla described that concept is the induced EMF, or current in a loop or coil or armature into a change in its effective area. Yes, effective area if the coil is rotated. If the coil is rotate, if the coil is rotate, okay, so effective area obviously the change. Effective area means these are the magnetic field. Okay, see that these are the magnetic field and crossing that effective area. if this you see that at that point, so the effective area will be 0, because that all be crossing that parallelly, okay, not cross or piercing that, okay, that's a skimming that effective area, okay, rotates, all effective area will be changed, okay. The effective area will change, okay. So coil loop is also called armature, okay. So if the coil is rotate the with a central if the coil is rotate with a angular speed, if the coil is rotate, this coil is rotate, if coil is rotates with angular speed omega and theta, the angle with theta also change, okay. And you see that if there is a rotation here, obviously there is a theta we change, these are the angular speed, okay. So here that is theta, this is the angular displacement, that is equal to omega speed into time, that's the angular displacement. Now we know that if the effective area will be changed, so B crossing that effective area means a flux, so the flux constant, that is a phi B, that is BA cos theta, now that is equal to BA cos omega t, now theta is replaced by the omega t, that's a phi B, okay. Now if I multiply both sides, is a n, capital N is the number of turn in armature, n be the number of turn in armature, n be the number of turns or winding in armature or coil, that is equal to, if I multiply n both side, n pi b, n b a cos omega t. Now differentiate both sides with respect to time, so n d phi b dt, that is n b a, so cos means here the sine omega t, and this omega t differentiate, that is get omega out. Now put minus side, minus in both sides, so that is a minus here, this minus now turn into plus, so that's the EMF, that is the EMF, that is equal to NBA omega sine omega t, and NBA omega, okay, NBA omega, this terms NBA omega is a constant, okay, and this is the maximum value of EMF or max value of EMF. Why? Because there is an angle, and the maximum value of angle is +1 or -1. If there is a +1, so that's the maximum value. If the -1, that's always minimum value. The total value actually depending on these. That's either +1 or -1. These are the angle. Angle is a +1 or -1. Okay, because the sine omega t, that is either +1 or -1. And if I say that the NBA omega, the another term is called epsilon 0, so finally get EMF equal to EMF 0 sine omega t. Okay, so there is a angular speed, and now there is another term, the omega, that is equal to 2 pi in nu. There is a linear frequency. That's the nu is a linear frequency, and now EMF equal to EMF maximum value sine omega means 2 pi nu linear frequency time t, okay, that's the EMF produced by that coil if the coil is rotate, okay. Is actually there's a AC generator if that coil is rotate. Mainly the important is if that armature coil is rotate. Okay, so how to rotate? That's the important concept. How to rotate? So if rotates, then produce energy. Okay, so rotate means how to rotate. There is a suppose maximum way in commercially, there is a thermal power station, okay, or hydroelectric power. So here in thermal power station, how to rotate? There is a flow of steam, high speed, flow of high speed steam. Okay, in armature, and armature now rotate, and armature rotate, and effective area will be changed. Area be changed. Okay, and these are steam generated by from water boiling with the help of coal burning. Okay, that's why these are called thermal power station. An example is Kolaghat power station in West Bengal. Okay, these are the thermal power station, Kolaghat power station. And what is the hydroelectric power? There is a dam. In the dam, okay, the falling water from top, they are very high. Water from top or very high in coil, fall in coil. Okay, so there is armature also rotate. Okay, if the armature also rotate, so the effective area will be changed. Now these are same concept. If armature is rotate, the effective area change. If the effective area change, so there is a EMF is generated here. EMF is generated. Okay, because the theta or omega t depending. Okay, so the EMF is generated. That's the for generating a energy potential here. Or another source from these are called nuclear power source, power generator, or windmill. These are the various types of sources here. Various types of source for rotating a power station here for rotating that armature. And there is a various process. Okay. And in a modern day, in AC generator, you see that in modern day, commercial AC generator here, AC generator, okay, produce 500 megawatt power. Okay, 500 megawatt. Can you imagine that? How big or how bigger energy power unit is? So there is a 500 mega means 10 to the power 6 means that watt. Okay, suppose you 5 into 10 to the power 6 times 100 watt, and now you see that this 5 into 10 to the power 6, 5, 1, 2, 3, 4, 5, 6. Okay, there's a 5 million. Okay, there's a 5 million bulb, and each bulb containing 100 watt. Each bulb in 100 watt. 5 million bulb can glow. Okay, in 500 megawatt power station in 100 watt bulb. 5 million 100 watt bulb glow in 5 megawatt power station. Okay, that's a commercial AC generator. That's a very huge or very large value. Okay, so there is a direction. There is another important concept. If the coil is rotate, so the EMF there is change. Now we draw a graph here for better understanding. Suppose there's a north pole of the coil, there's a south pole, and that armature is the north, there's south, that's the armature. Now look like this. These are the armature. Okay, so magnetic field north to south, and suppose these are the A, B, C, D area in that direction. Okay, if the area and magnetic field both are in same direction, so obviously theta be that 0 degree. If theta be the 0, so EMF, that sine 0 be the 0, sine 0 degree be the 0, that means EMF be the 0. So if I plot here, okay, and y-axis in induced EMF, you see that at this position, so no EMF here. Now north and south, suppose rotation in that direction, okay, the clockwise direction. Now A, B, C, D. Now the area is downward direction, and field in that direction, the angle is 90 degree. So sine 90 be the 1. So there is a maximum EMF here. That case, so that here that maximum EMF here. Here theta equal to 0 degree. Here theta equal to pi by 2 or 90 degree. So here is a maximum EMF means plus 1. That's the minus 1. Okay. Now, if the change in the S coil okay, so the area, now there's A, B, and there is C and D. Now see that carefully, area in left side and B is in right side. That's the area. Now the angle be that 180 degree. Okay, so sine 180 be the 0. So again the fall, EMF fall here, that is a pi, at pi there is a no EMF here. Now there is a north, there is a south, the coil then rotate. Now that A, B, C, D, so the area in A and the B in that direction B, the angle these, that is 270 degree. 270 degree. If the angle is 270 degree, so means sine 270 is a minus 1. This represent a minus 1. That is theta equal to 3 pi by 2, 270 degree here. There is a maximum minimum EMF of minus 1 degree, the negative direction. When becomes 0, now back to here. That is a 2 pi. Here we get 0. That's the EMF, and these are the sinusoidal cycle. So that's why these are the AC, alternating current. The plus 1 and some 180 degree difference, we get a minus 1. So plus 1, 180 difference, they get a minus 1. That's the AC generator. Clear? And there's a time period, and if you see the time period is, that is a T T by 4, therefore that is T by 2, that is 3 T by 4, okay, and that is a T full cycle. That's the full cycle, that is the half cycle, 1/4 cycle, and 3 by 4 cycle. Okay, that's the AC generator. Clear? That's our syllabus. Okay, today we clear the concept what is a AC generator, what is a inductance, what is self-inductance, and what is a mutual inductance, and what is a motional electromotive force. That's a very important concept. Today all are in summary here, or all discussion here. If you doubt, always ask in comment section. So next class we discuss the new concept, new chapter. Okay, thank you.